Sorry again. The connection is back, so I shall continue. Right. The problem is we like to minimize this function g of b. Okay? For which b this is minimized. So look at g of b. Okay? And then this is multiply this part. Okay? Multiply this part. Then what you see is x squared minus 2b times x and plus b squared. Is that right? This is a function g of b. Now we use the linear property of expectation. And then we're talking about b. Okay, this is a variable. Then what about this? This is, of course, e of x squared, second moment, and minus 2b times c of x, right? And then plus b squared. Okay, this is a function. Look at this as a function of v. Then we like to differentiate, okay, this guy. So what is the derivative of g prime of b? B. What is this? G prime of b. This is a constant, so this is 0. Okay, this part b is here, so negative 2 times of e of x, and negative 2 e of x. Okay? And then this part is a 2b, okay? 2b. And set this is equal to 0. Okay? This is equal to 0. So what is b then? E of x, right? E of x. Or you can say this is mu. Okay? At mu, this derivative is 0. And then one more thing we have to check. There is a second derivative. Okay? Second derivative is what? This differentiated with respect to b. This is constant, so 0. And this is 2b, so this is 2. And then this is positive. So g of mu is the minimum, right? We can say g of mu is the minimum. So this is our conclusion. And then what? What's next? This is mu, okay, mu. Then this quantity is called the variance. Okay, we'll call this value when I should write this is the variance. Okay, variance. G of mu is called the variance. Okay, we'll see. Definition of variance is given by this. But the idea of variance is given by this. So we'll see later. Okay. So we'll do more examples. This is problem 222. Okay? 222, number 222. X is a random variable subject to the probability mass function given by the absolute value of x and plus 1, and then this is squared, and then divided by 9. X is negative 1, 0, and then 1. Okay. This is the probability mass function. What does this mean? I.e., what is the value f of negative 1? What is this guy? F of negative 1. Negative 1 comes here, that is 1. 1 plus 1 squared is 4, 419. So 4 nines, this is f of negative 1. And also, if you plug in 1 here, then again 1 plus 1 squared. So this is equal to f of 1. So f of negative 1 and f of 1, those are 4 nines. What is f of 0? 0 is here, then 1 nice, right? And you see that this plus this is 1. So this is the probability mass function. Then calculate the expected value, or mu. Okay, mu. What is a of x? Let's calculate e of x. By definition, the sigma of x times f of x times f of x, and then x is negative 1 through 1. So when negative 1, what is coming? Negative 1, then the negative 1 times the probability, it's 4 nines. Okay, and secondly, the value is 0, okay, 0. So 0 times 1 ninth. And plus, finally, 1 times 4 nines. Okay, this is a expected value. We agree? The value of x and times its probability. Value of x times its probability. Value of x times its probability. This is our expected value, or mean. And obviously this is 0, and this opposite, so this is equal to 0. Okay. Mean is 0. And that's what we can have. Mean is 0. The next one, okay, next one. What is the second moment? X squared. What is this expectation? E of x squared. Then if I write negative 1 squared times 4 nines, and plus 0 squared times 1 nines, and plus 1 squared times 4 nines. Okay, this is a 1. This is 0, this is a 1, this is 1. So will be 8 over 9. Okay. And then finally, what about the expectation of 3x squared minus 2x plus 4? Okay, let's calculate this expected value. Expectation of 3x squared minus 2x plus 4. Okay, this is by the formula. This is 3 times of expected value of x squared and minus 2 times of expected value of x and plus. This is a constant, so constant is just constant, 4. Okay. So this is a 1. And we know that this is 0. This is 8 over 9. So this is equal to 3 times of 8 over 9. And then minus 2 times 0 and plus 4. So is equal to what? 8 over 3 plus 4. 8 over 3 plus 4. So 20 over 3. Okay. That is the answer. Okay. Another example, 226. 226. The random variable is subject to the probability mass function. In this case, x can be 1 through infinity, 1, 2, 3, dot, 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 up to infinity. In this case, the probability mass function is given by 6 divided by pi squared x squared. Pi squared x squared. And then x is equal to 1, 2, 3, okay, dot, 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 up to infinity. Now looks weird. Why we have 6 over pi squared? There's a reason. So why this is a probability mass function? Well, sum of this guy for x is equal to 1, 2, 3 up to infinity is 1. do you see that? Okay. See, first of all, see this f of x, and then x is equal to 1 to infinity. We have to check this sum is 1. Okay, this is equal to, this part is a constant, so we can write 6 over pi squared. Okay. And then sum of the 1 over x squared, x is equal to 1 to infinity. This should be 1, but do you see why? That means this sum must be the reciprocal of this guy, that is pi squared over 6. Is this so? This is pi squared over 6. Did you know? This is pi squared over 6. Oh my gosh. Yes, that is correct. And then this is equal to 1. Okay. And there's a very famous story. We're writing x as a variable, so it's not so comfortable. But if you write this way, 1 over n squared, and then n is equal to 1 through infinity, maybe this is comfortable. This is 1 over 1 squared, and plus 1 over 2 squared, and plus 1 over 3 squared, okay, plus dot, dot, dot. And this is our sum. And then this was first derived by Euler. Okay, Euler is a 18th century mathematician. And then he was the first to find this sum. This sum is a pi squared over 6. And that's what he did, pi squared over 6. Due to Euler, Leonhard Euler. He's a 1707 to 1783. Okay. 18th century mathematician. He has lived up to 76. When he was 35 years old, and then he proved this one. Originally, this was based by the Jacob Bernoulli. Okay, Jacob Bernoulli, the big brother of Bernoulli brothers, and he was counted as one of the founders of calculus. So together with his young brother, John Bernoulli and Jacob Bernoulli, they are considered as the founders of calculus. And Bernoulli, the big brother, died in 1709. 1709. 2 years after Euler was born, he died. He raised the question, but he didn't see the answer. So about 30 years later, Euler has proved this theorem. Very nice theorem. Okay. But this is a prize-winning problem, and then of course Euler got the prize, but he sacrificed his right eye. He did 4 nights and 5 days straight. He did 4 nights and 5 days straight. So yeah, of course he slept a little bit, but mostly 4 nights and 5 days. So his right eye became very weak, and then eventually he lost eyesight. So he sacrificed his eyesight, and then he found this formula. Okay, that's a story. I don't want to spend that much to sacrifice my eye. I don't want. Anyway, so this is the one. So we see that this is a probability mass function. That's what we figured out. Then our question is, what is the expectation of x? Okay, this is a question. How do you get this value? This is by definition. By definition, x times of 6 divided by pi squared x squared. Right. And then x is equal to 1 through infinity. This is the expected value. If you simplify, then 6 over pi squared goes outside, and then x and x squared, so this is 1 over x. So 6 over pi squared outside, and then sigma of 1 over x. X is equal to 1 through infinity. What do you think? Unfortunately, this is infinity because this sum is infinity, okay? This sum is infinity. So this is infinity. That means expectation doesn't exist, okay? Expectation doesn't exist. This is the conclusion. Yeah, sometimes this happens. And one more thing I'd like to mention. What about 1 over x squared? 1 over x squared. This is by definition 1 over x squared and times the probability mass function 6 over pi squared over pi squared times x squared. Okay. X is equal to 1 through infinity. And again, we have 6 over pi squared that is outside of the sigma. And then inside is 1 over x to the fourth. Okay, x is equal to 1 through infinity. Okay, do you know this sum? This is again a famous sum. This is not pi squared or pi to the fourth over 90. This is pi to the fourth over 90. Pi to the fourth over 90. This is a well-known sum. Again, this is done by Euler. Okay, Euler figured out this guy. And then so this is equal to, you can simplify pi squared on top, and then 15, I guess, 15. So pi squared over 15. This is our expected value. We can say this kind of stuff. Not necessary, but if you memorize these guys, you're great. Okay, this is pi to the fourth over 90. Okay, x squared, 1 over x squared is a pi squared over 6. Fourth, pi to the fourth over 90. You can have 6, 8, 10, 12, up to 28 Euler calculated. And then in each case, we have pi to the fourth, pi to the 6, pi to the 8, and so on. And something underneath, the denominator is an integer. That's what this is. Okay, then I think we're done with this section. Do you have questions? I did two, mathematical expectation. Up to this section, you have the what did I say? Up to this, up to this section 2.2, we have the midterm. Okay, so 1.5 and 2.1, those are due this Friday, and 2.2 is due next Friday, and then midterm will cover up to 2.2, section 2.2, and then I shall post a sample exam by the end of this week, and then I shall do a review on Wednesday next week. I shall go over all the problems on the sample exam. Okay, then you can get used to the actual exam. Not same, but similar. Any questions so far? Are you okay? All right, then we can go to the next section. Next section. 2.3. Section 2.3. It's a special mathematical expectation. Special expectations. So starting from random variable, okay, a random variable is given, okay, and then space of x, this is a range of x, that is consisting of finitely many numbers, u1, u2, up to u sub k. Okay, this is the space of x. And then f of x is given as a PMF. So x is in the space of x, s sub x, the PMF. Probability mass function of x. And now necessary, the sigma of f of x, x is in the s sub x, this is equal to 1, necessary. And we define the mean mu. Mu is a expectation. This is x times f of x, and then x is in s sub x. This is called the mean. Of x, e of x, same as e of x. This is easier to say, mu. Mu is a mean or average, you can think. Then the first moment of x about the mean mu. What? Sigma of x minus mu n times f of x. You consider this sum. And this sum is called the first moment. Okay? The first moment. The first moment of x, okay? Of x about the mean mu. About the mean mu. Okay, this is a name. The first moment of x about the mean mu. Okay. This is the first moment. Okay, this is from e of x. About the, if you say about, then about the origin or 0. This is the first moment about 0. This is the first moment of x about mu. We subtract mu from x. Okay, that's the one. That's the reason. If you subtract 1 from x, then this is about 1. If you subtract 3, then about 3. And that's the meaning of this. Then can you get this value? Actually, we can write this guy as in this notation. This is x minus mu. Do you agree with this? E of x minus mu. Do you see? This is a variable, okay, new variable x minus mu. So this value will come here. X minus mu, then x minus mu. Okay, so this sum is an expectation of x minus mu. But you can write this as e of x and minus mu. What is this value? What is e of x? Yeah, this is mu. This is mu. So mu minus mu, that's going to be 0. Yeah. So that's the value. First moment of x about the mean mu is 0 necessarily. That's what we see. Okay. Then next step. Okay, next step. We define what? The variance. Okay? Variance is denoted by sigma squared. Okay? Sigma is a Greek letter of S. Okay? S. Sigma squared. And then this is a variance of x. Another notation, variance. Okay? Sometimes some authors are using just v of x. Okay? But this author is using bar, okay? B-A-R, B-A-R, indicating variance. And then this is defined by the expectation of x minus mu squared. Okay? we have seen this quantity, okay, x minus b squared, and then this quantity is minimized when b is equal to mu, and we're taking this guy, okay, mu, so x minus mu squared. This is called the variance. Variance of x, okay, of x. Well, if you like to use the moment, okay, then this is a second moment, because this is 2. Second moment about mu. Okay? This is the variance of x, okay, in one sense, and then this is also the second moment about mu. Okay, this is the second. I'm gonna write 2. Second moment about mu. Okay, this is another way of saying the second moment about mu. Okay. Variance is the second moment about mu. This is a definition. This is a definition. Definition. This is what a definition. Okay. And then the reason why we write sigma squared is we need sigma. Okay, sigma itself. This is a positive number. Okay. This is a positive number. Okay. The standard deviation of S. The standard of x. Okay. Sigma itself is called the standard deviation of x. What we are doing is mu is the average value, okay, average value. Then this quantity is the value of x is how far from the mean mu. To get the actual, meaningful value, we need a positive number. An easy way is just square. If you take the absolute value here, maybe that means something, but not like this. Square is the calculation is very simple. It's a square. So this quantity is the x is varying from its average. How far is it staying away from the mean mu? And we're taking an expectation. Then what is the average of this thing? The thing is variance. And then actual value is this is a square number. This is a square number. So we like to have the original number kind of. So that is sigma. Sigma squared. So sigma is the original number kind of. And this is indicating how far from the average mu. And then we will see very interesting stuff using sigma and mu. Okay. So in probability theory, for the random variable, mean mu and variance or standard deviation, those are the two most important numbers. For the random variable x, the mean mu and then standard deviation or variance sigma squared, that's the most important numbers. So that's what this is. Okay, one more thing. We have time? Okay. So 15 minutes or so. Okay. I like to calculate this one. The thing is, if you find mu, and then if you calculate sigma squared using this formula, okay, then each time we have to make a difference, x minus mu, and then square, okay, x minus mu and square, x minus mu and square, and then we add. But there's a little bit simpler way. Okay. This is a formula. Sigma squared is equal to expectation of this. But we're gonna multiply this, okay, multiply this. So then this is x squared minus 2 mu x, and then plus mu squared. Is that right? I just multiply this guy and this guy. Then we can separate this sum as e of x squared, okay, minus 2 mu times of e of x, and plus mu squared, right? 2 mu is a constant, so going outside of the expectation. But what is this guy? E of x. This is mu, right? Mu. Then negative 2 mu squared and plus mu squared. So will be what? E of x squared minus mu squared. Okay, so this is our formula, okay? Easy formula. Sigma squared is calculated as second moment minus the first moment squared. E of x squared minus mu squared. This is an easy formula. So data is given, then we just make a sigma square and then multiply by probability mass function. And then sum is done, then subtract mu squared from that. Okay, that is a variance. So this is an easy way to calculate. So now, let's calculate. Okay, let's calculate the mean and then variance. Okay, for some particular random variable. Okay, so let's do. So to calculate, we're going to use this formula. This is easier. So this is a text example. Okay, but interesting. So we're going to take this. X is a random variable subject to the probability mass function. Oh my gosh. I'm sorry, this is X. Okay, this is X. This doesn't look like X, but it is X. Okay, X, f of X. This is 1 over m. Okay, I was affected by this m. Uniformly, so we can assume that X is taking values 1 to up to m. Okay. For each x, the probability mass function is 1 over m. So this is a uniformly distributed random variable. Uniformly means for each case, we have the same probability. So uniformly distributed. It's like when you draw a die, okay, die, 6-sided die, then 1, 2, 3, 4, 5, 6 will appear with the same probability 1, 6. And that is the case. The x is equal to 1, 2, 3, 4, 5, 6. And then each probability is 1, 6. Okay. Uniform case. So let's calculate. Okay, we have 10 minutes or so, right? Can you get the mean mu? E of x. E of x. How to calculate this guy? This is sigma of x, and times the mass function is 1 over m, always. And x is equal to 1 through m. Okay, this is a 1. Then what is this sum? Sigma of x. X is equal to 1 through m. Okay, that is of course, m times m plus 1 over 2, right? And times the 1 over m. This is a sum of 1, 2, 3 up to m. So that's going to be this. You know this formula. And 1m, they're cancelled. We have m plus 1 over 2. So this is a mean mu. Then we like to calculate the variance. Then to calculate variance, if we use the formula, okay, formula means definition, then we have to calculate x minus mu squared. 1 minus this, and then squared. 2 minus this and squared. We don't like to calculate that way, right? 1 minus this, and then squared. Oh my gosh, I don't like it. So instead, we better use this formula. E of x squared minus mu squared. So what is the E of x squared? Okay. We like to calculate. So this is sigma of x squared and then 1 over m, and then x is equal to 1 through m. This is what? Sigma of x squared. Sigma of x squared. That is we know the formula. That is m times m plus 1 times 2m plus 1. Remember this? Okay. And then divided by 6 and times 1 over m. So this is equal to m and m are cancelled. We can't cancel m plus 1 and then 2m plus 1. We can't cancel this part. And divided by 6. Okay? This is a second moment. So using this guy, we can calculate sigma squared. Use this formula. Okay? This formula. E of x squared minus mu squared. This is the way it goes. And this is equal to m plus 1 2m plus 1 divided by 6 minus of m plus 1 over 2 and then square. Okay. And probably you can calculate this because m plus 1 is a common factor, and then it's not so bad, I think. And then if you do this, then we have m squared minus 1, m squared minus 1 over 12. And this is what we have. Please check yourself. M plus 1 is a common factor. Yeah, see that this is a m plus 1 times m minus 1. That is a common factor. M plus 1 is a common factor. And I simplify other part. Then we have this. Okay. Okay. Then interesting question is not here. Okay. Then next question is if mu is equal to sigma squared, then what is m? Okay, this is the question. This is actually a problem 237, okay, number 237. 337. This is a question of the problem 237. Okay. If mu is equal to sigma squared, then what is m? That is the question. Well, it's easy, right? If mu is this guy, sigma squared is this guy, so equate these two guys. Okay, equate these two guys. So what we have is m plus 1 over 2 is equal to m squared minus 1, and then 12. Okay. Then we can cancel by m plus 1. M plus 1 is here, m plus 1 is here. So we have 1/2. Okay, 1/2 is equal to m minus 1 over 12, right? This is the one. So can you see m? Okay, 2 and then 12, so times 6. So this must be 6. M minus 1 is 6, so m is 7. Okay, so in this way we can figure out this number m. This is a problem number 237, right? We have 3-4 minutes. One more thing, then I will be done. Okay, one more thing. One more thing is, okay, the random variable x is subject to the mean, mu. I'm going to write mu sub x, and then sigma x squared. Okay, these are the ones, mean and then variance. The random variable has mean mu x and then variance sigma x squared. And then we have one more, another random variable. This is ax plus b. Okay, ax plus b. Then can you get the mean of y and also mean or variance of y? And those are obtained by mu sub x and sigma x squared, obviously. So let's see. Then we're done. Then I calculate mu sub y. Okay, first of all, this is e of y, and this is e of ax plus b, right? Then a of ex plus b itself. So this is a times mu sub x plus b. Oh, it's easy. It's easy. What is interesting is variance of y. Variance of y. Variance of y. How do you get variance of y? The b is irrelevant. Only a is involved, and then a squared will come out. So you can see sigma y squared. Okay. Variance of y. Variance of y is by definition. I'm going to use the definition in this case. Y minus mu sub y, and then squared, and then it's expectation by definition. Then y is ax plus b, and then mu sub y is a times mu x plus b. You see that b, this b, and this b, they will be cancelled. B minus b, that is 0. Only ax minus a times mu x. That part is squared. So ax minus a mu x. Okay, this is squared. And we take the expectation. Do you agree? And then this is, we can factor a squared, and then times x minus mu x squared, mu sub x squared. So that a squared will come out, a squared times expectation of x minus mu x squared. Do you agree? Oh, I'm writing too tight. Here it is. But what is this? This is exactly the sigma x squared, right? So this is equal to a squared times sigma sub x squared. And this is a result. What I mean is when you have random variable x and then random variable y, that is a linear function of x, so ax plus b. And its mean is simply a mu x plus b. But variance, this b is irrelevant. Okay? This b is irrelevant. Just a is relevant. And then a squared comes out. A squared comes out in times sigma x squared. This is the formula. Okay, that's it. Right? Any question? We're done. If you have questions about homework, then you can stay and ask me. If not, then you can leave. So have a nice day. Okay.
Thank you. You too.
Okay.